So thank you everyone, and welcome to this talk. So I'm really glad to see all of you in this room. So as she was saying, my name is María Gómez. I'm a developer. I'm a tech principal at ThoughtWorks, currently working in Barcelona, and I'm a full stack developer. I've been working all my life on building software for different organizations, and in my 6 years at ThoughtWorks, a lot of the things that I've done is help also or work with organizations on improving the way they are delivering their products. Guess we need to do a full disclaimer. I'm not a hardware engineer, and I'm not also a low-level engineer. Like, I don't program in C++, or I don't know how to I guess at some point I knew how to develop a program and create a driver, but right now I don't know any of that. But what I did in the last year or so was to help or to work with a couple of companies and a couple of teams on improving the way that we're not just building software, but also integrating with the hardware that was where the software was embedded on. So this is me, as I say, so before we go into the actual talk, I think it will be nice to look a little bit around the history of what we think, or how, I guess, agile process and agile software delivery has moved. When we talk about continuous delivery and we look at the definition of Jeff Campbell, who was the first person, or I guess the person who wrote the book on continuous delivery, they defined continuous delivery as the ability to get changes of all types into production or into the hands of the users safely and quickly in a sustainable way, right? And for, I guess, teams that are developing high-level software, web apps and things like that, this made a lot of sense, and a lot of those teams, a lot of those organizations were, adopting certain practices. Because we started here, where software delivery was treated as, any other like civil engineering projects, and it was a really long process and not really easy to adapt or easy to change. And then we moved into, start creating these agile teams that were very efficient on the processes, in development processes, how they test their software and how they test the things that they build. But then there was always this, what is called the last mile, which is, all of these other processes that needs to happen before things get into production. And continuous delivery kind of try to put all of these things and move them in an earlier stage. So you can start delivering features in a constant manner. So it's a constant flow of features that are being put or are being released to the customer or to production. And that's what most of the software companies, well, I wouldn't say most, sorry. A lot of the software companies are doing, but most of them are trying to get to, right? And in some cases, you get companies that are deploying to production every single day, multiple times a day, right? But then I went to, as I say, these couple of places and these couple of organizations, and I realized that when we talk about, a lower level of development. So when we talk about embedded systems, or when we are looking at integrating with certain pieces of hardware, then we are in a less mature space. So the motivations for this talk was to actually say, okay, so what are the things that I saw in those places, and what are the things that we try to make that delivery and process more agile and more efficient for everyone. So when you are in in software projects, or I don't know how many of you are used to work with hardware and software on a daily basis. Like your job might be either to develop embedded systems or even work on things that are interacting with sensors, hardware. Cool. Okay. So I guess it's the rest of you are software developers, and what you do is kind of, build an application. Yeah, okay. So then, cool. So then you're in the same boat as me. So yeah. So so then as a developer, as a high level. Sounds really weird, but yes, as a high-level developer, when I'm used to work on, Java, Ruby, or something like that, right? So building applications, web applications. Then I'm used to have something, an application, and then I'm deploying a new feature, and then really kind of very straightforward. I have a pipeline and stuff, and then that new feature will go into production, right? But then when we are talking about applications or systems that have some hardware components, then that's a bit more tricky. It's trickier because it needs to have, there needs to be some integration part in there. So continuous delivery became a bit more, it became tricky on that, right? So continuous delivery, more on so not at the definition, but then in practical matters, is more than just having a pipeline. So I like this way of representing what continuous delivery is, because it very clearly states what are the different aspects that you need to take into consideration and you need to work on as a team and as an organization. So there are things like architecture, how do you release, and also how your organization is changing and adapting to this way of working. So I'm going to go through a few of them and tell you what we try on those teams. And this is one of the multiple maturity models that you can find and that you can use to self-assess how you as an organization are going through that path. So starting with architecture, right? So architecture is taking care of the important stuff, whatever that is, right? So and that's valid for software and that's valid for hardware, right? So and the person who get this nice definition is one of the people who was working really hard and working really closely in the XP days, the very beginning, so in the early 2000s and stuff. So when we are designing systems, we normally have some kind of an idea of what the system is going to look like, right? So we might say, hey, we need to build an e-commerce site or an e-commerce platform. So there will be, a payments component. There will be some kind of catalog and stuff like that. And I will get some, I will expose functionality, and there might be some services in there, or it might be there might be some databases. There's certain things that you are starting to agree on, and then you will try to adapt as you go along, because you will know more as the time passes, right? So you will use things like evolutionary architecture when you are saying, these are the things that I know now, and I'm making my decisions. But then there might be that in 2 months I know something different, so I need to make sure that I adapt. So I don't know, I'm not going to make a lot of upfront decisions and just make the important ones that I need to make now, so I can move forward. And then when the moment comes, I will take other decisions, right? You will take care of certain concerns that are important for you and put them in some kind of degree of priority, and that will allow you to make all of those decisions, right? So maybe compliance or security is really important for the system that you're building right now, but maybe in 4 months, 6 months, something else is even more important. So for hardware, I guess you follow, or you can start to follow the same approach, and you can say, an envision on my brief or what I'm trying to do, my vision or the vision of the product is to build some kind of system that connects multiple things within a house, right? So I know that what I'm thinking is that I'm going to use this type of sensors, and I'm going to have maybe an application where a server where all those sensors are going to communicate to, and then there's going to be some logic in there, and this is how I'm going to be. This is the protocol that they're going to use to communicate and stuff like that, right? But then maybe after you or after the team is starting to make some tests, some of those assumptions might not be true or might be better ones. So one of the first challenges that we faced was that understanding that or embracing change is something that some of the people working on hardware are not that used to do, and they used to make decisions that are actually quite hard to change, which, yeah, sometimes it's fair because you're actually fusing that decision into a board, so that's obviously really hard to change. But the same approach that you take in software when you are trying to just leave decisions to the last responsible moment are things that also can be done when you are doing hardware, and also can be done when you are building a system that integrates with different peripherals like sensors and stuff like that. There is also something called digital twin. Sorry, they're called digital twins. God, I forgot the name. I think so. So there's something that a lot of companies, big organizations, are doing now, or they have been doing for a few years, which is, they don't actually commit to create the hardware until they have proof using some mocking model. So they use things like machine learning and AI to actually create some models that will mimic what the physical systems are going to do. So then they can develop and they can create that digital copy of the physical environment. So they can develop against that and prove and experiment and do a lot of these spikes and things like that. And then once they see or they feel that this is the right decision, that's when they start committing to actually transforming it into hardware and making the physical boards or whatever it is that they need to make. Another important thing is quality assurance, which is how do you ensure that the product that you're putting in there is not just behaving as you wanted it to behave, but also is the right thing for the customer, right? So, and this is something that in every single project is always really, really interesting to look at, right? Because you might have multiple people looking at this from different points of view, and you need to, or teams needs to find a way where they can collaborate with this, right? Quality is not the responsibility of just one team, the QA team. Quality is the responsibility of everyone, right? So in software, you might go into, having different type of tests for different type of concerns. So you might write unit tests for, as a developer to try and test the small parts of your code. And then as, you might write different type of tests and you go higher in level of abstractions, right? In hardware, you can do exactly the same, right? So one of the first things that we did was to sit with the developers that were developing the firmware and the software that was embedded in the boards, and teach them or help them write tests, help them write unit tests. Most of these developers and most of the embedded systems are, well, not most of, but a lot of them are written in C++, and they are surprisingly, or at least I was surprised, there's plenty of, or quite a interesting range of tools that you can use to write tests in C++. So there's Google tests, there's CPP units, and there are actually quite a lot of examples out there that you can use to write and to even TDD your firmware, which, it's quite amazing. And then start to think about how you're going to prove the quality of that piece of software that you're building and the hardware that is coming with it. And that's the most tricky bit, because you need to, sometimes to prove that, you need to actually put that software into that hardware. So one of the things that we did as part of our pipeline, our Jenkins pipeline, was actually have a dedicated Jenkins client that was agent that had plugged 2 of the boards that we were using. So our project, probably should have said that before, our project was building a device for the car that then had a communication with another device, which it was an Android device, and it will allow the driver and the people in the car to change certain things, like the temperature and stuff, right? So, so basically, what we ended up doing was one of the stages on our pipeline was a Jenkins agent that was connected to these 2 boards. So the board for the device in the middle of the car and the board that contains the Android system. And we actually ran some tests in there. And we start looking at what are the things that we could test and what are the things that we could assert on. Because, you know, you're saying, oh, I want to increase the volume of the speakers. How can I test that? So you can test that you are sending a signal sending a request through that Android app to the board, that the board is receiving the signal and is sending you back hey, the volume is now 10 and before it was 8. You can even test that, you know, if you have a connection to another thing, like for example, if there's speakers, you can actually connect to the speakers and get the sound that the speaker, so the frequency of what the speaker is playing, and see that it's within certain range, which is the one that you're expecting, but for the volume that you have been setting. So, you know, start to look for innovative ways in which you can automate the testing of that, because that's going to save you a lot of time, and that's going to save, that's also going to increase immensely the confidence that you have on the things that you're working on. Hardware, and if you're like building your own boards and stuff, has another thing called the board bring up, which is something that I'm not totally foreign to it. I have experienced it because there were people working on that next to me, but I'm actually not an expert on. But you know, this process is normally quite slow. So, you know, again, trying to find ways where you can speed up this process, parallelize it, and automate it, some of them is going to be quite crucial. And then, you know, the same thing as with any software process, with any software project can apply here. So just because it's an embedded system, that doesn't mean that you can't actually, it's even more important that you look for certain things like memory leak or how the software is actually performing, or you know, how are you writing the code and stuff like that. So the normal things around static analysis apply here, security. So you want to make sure that you know, there's nothing more dangerous that there's a lot of things that are very dangerous. But you know, you think about it. If you have, you know, if someone can hack into, like, you know, your Alexa or whatever, that's pretty frightening. So you know, you can also add security tests and test how you are hardening your devices. Now, continuous integration is one of my favorite things to do. So continuous integration is this loop when you are developing software, you're testing that software, and you maybe even deploy it to an environment and then do more tests on that environment, right? And it's, you know, for people writing software, is kind of, for like high-level developers, it's kind of our bread and butter. Like, how many of you are currently doing continuous integration? So, you know, most of you, right? So continuous integration is this process in which we say we are a team, and each one of us might be working on something different, so we need to make sure that we're integrated and that what we are doing is actually not just fulfilling my requirements, but also not breaking the rest. So, you push your codes frequently, hopefully once per day. There a pipeline that gets triggered that will make some tests, and you will get some feedback. And if something breaks, the pipeline stops, and then the team will come together and fix it, right? So this was quite interesting because most of the developers that we work with, some of them, they never write a test. So that was something that it was, new to them, but also they were very used to work on their own branch, weeks at a time, not really integrating with anyone else. So there was a lot of, trying to work with them on identifying how to break really big features into smaller ones that could be something that can be moved into or pushed into a branch, a continuous integration branch every, a little bit more often, that's every 3 weeks. But we managed to do that, right? So like at the end, even if you're writing something that connects to a sensor or something like that, I'm pretty sure you can identify very small things that can be pushed and that you can test how they're working. Which take us to which take us to, what is coming next on, this one. So yeah, we are talking about continuous integration and how they will trigger a pipeline, so what that pipeline will look like, right? So this is a normal pipeline that you will have in your software projects, and you can also have in your project that is integrating with a hardware component. So as you are trying to reduce the lead time by automating as much as you can on this pipeline, and that's what we try to do for this project. In this team, at least, they were used to do releases every 6 weeks. So the lead time from a commit to production was 6 weeks, and they wanted to reduce it to 2 weeks. So, and they have a lot of manual process, and this wasn't even their pipeline, right? So the pipeline was, I'm committing my code, someone goes and tests it, and then there's a few other people that go and test it, and then that's it. So, and all of that take at least 6 weeks. So, we put the stages on the way, like, testing and stuff, but we also make sure that the deployments to various environments or any kind of state was automated to also reduce the lead times of those. Because you want to have something like this. Normally, pipelines are not one straight line. They are multiple lines coming together and doing some kind of stuff, right? So this one is kind of an example of what we had in that. So as I said before, we were building a device or a system that had 2 physical devices. And what we did was we have on one side we have an Android device. So we actually were building our own version of the Android operating system. And that's, I don't know, that's like 100 gigabytes or something, I don't know, that's massive, it's really, really big, right? And there were multiple repositories that contains, multiple layers or multiple things that you can chain on Android. And then you need to compile them both. You need to compile them all to actually get the actual operating system, which is what you kind of flash into the board. And the same thing with the other board, which we call the Linux board, because that one just has a normal Linux distribution. So we start looking into, doing this process without automating the process, but just in normal machines will take us probably days, because just building ASP takes you like probably I don't know, 8 hours, I don't know, in a normal machine. It's really, I mean, it's not that it's slow, it's just that it's a lot of stuff to compile. So what we started using was, we started looking at things that could make us go faster. One of the things that we found, well, no, not one of the things that we leveraged was AWS. AWS can give you really powerful machines. They're really expensive, but you can have them. But that doesn't mean you need to spend a lot of money, because you can also just use them when you need them. So you can just spin them up to build ASP, and then you can destroy them when your ASP is done. And also you can automate that through Jenkins. So Jenkins, and actually you can automate that through the AWS command line, through their CLI. And if you are using Jenkins, Jenkins has a plugin, but you can actually do that in the UI, or you can do that through a Jenkins file. So you can do that as a code also. So that's what we did. So we created an AMI that contained what we needed for. Actually, our AMI was really simple. And then we had a Docker container that contained all the dependencies that we needed for building ASP. So it has like Java and some other stuff. And then part of our pipeline was that every time there was a change on one of the repositories that were part of the ASP, we would trigger that job. It will go. It will start an instance. It was M42X large, which is massive. And it will just build that thing. And I think it was taking like around 45 minutes or something like that to build the whole ASP from scratch. So do a clean build. When we were doing no clean builds, so when we were not touching the kernel, you could actually just do like a refresh, and that was much faster. That was like maybe a couple of minutes or something like that. So we did that. So that was a problem solved. The same with the Linux, with the other board, that was the Linux board. In that one, we were building a Linux distribution. We were using Yocto, which is it's a tool that allows you to also build distributions kind of targeted to embedded software or embedded distributions. And that one has a concept of recipes, so you can have like the core recipe for Yocto, and then open embedded. So the core recipe for open embedded and stuff, and then you can add your own recipes if you need to add some drivers, or you need to configure the operating system to do whatever, or if you want to add an application that runs on that system. So that was the other thing. So we had, so in that example, repo B, for example, was an API that was then added to the distribution running on the board, and then repo C and all the other ones were just recipes that then will be built in a later stage through Yocto. And we follow the same process. Again, building Linux is also a really time-consuming and very demanding process. So we also reuse Amazon and make use of those type of instances to make our life much easier. Then, very similar after that, we will publish all of our artifacts in S3, so they were available for later stages. And then at some point, we did this fan in that is coming here. So at some point, when these two things were working or were triggered, then we actually ran. So we flashed them into the boards, and we actually ran all of these end-to-end tests that were giving us the confidence that we needed that we were releasing correctly. And then, the company had other things, like they needed to have the release notes in a certain manner. They needed to have certain reports, as in test coverage, compliance, and a lot of other tests that were run. Those were also automated through the pipeline, and those were also then the reports in HTML were packaged up with the rest of the release. Yeah, this is kind of that wasn't exactly the one, but it was very, very similar. So we had a Jenkins server that was the only one that was running 24/7, and that was just a medium instance. It didn't have, I think the only job that it had was actually just running unit tests and stuff like that, so very, very low. And then we will had a bunch of Jenkins agents that were targeted to do these really big compilations. And as I say, you can have them. That's an estimation, but 5 hours per day. That costs, I think our bill at the end of the month was maybe $200, so very, very small. And then a Jenkins agent on-premise, that was the one where we plug our boards to actually test it. Now, I'm talking about how these things were prepared for release. So at the end, you wanted to release that thing to the customer. And the customer, like with anything, the customer needs to understand how or when the functionalities are going to be ready for them, or as a user, I would like to see things coming up in, in some kind of order. Well, it doesn't need to be order, but I will need to keep receiving some functionalities, right? And sometimes we think that because we're doing agile, we don't need to do planning, but that's not entirely true. So even for a hardware project, or for a project that has a hardware component, you also need to plan what are the things that you're going to do. So, what are the features that you're going to be, or functionalities that you're going to be releasing? What is the priority of those? You don't need to plan 6 months in advance, but understanding what are the things that you can do in the next few sprints. And also, if you need to do like a firmware release, or even a rework, so you're getting new boards, because there's been some rework done, or they've been adding some new stuff. Where are you going to get those boards? When are you going to be able to do also those type of releases? And the last thing, which was also very interesting and very, it was somehow challenging, but it was very interesting, right? Like, you get, like with everything, I guess, or with like every organization that is going through continuous delivery transformation, there needs to be understanding from the business that doesn't mean the developers need to work in a certain fashion. That means that everyone in the organization, or most of the people involved on delivering that product, need to also adapt and change certain things, right? So the DevOps culture is something that we are very used to talk about, but it needs to be something that kind of spreads on all levels of the organization. So and it just goes for operations people, although there might not be that many, but mainly QA or validation, whatever it's called in the organization. They seems to have, or they normally have a really big and important validation process for, you're delivering hardware, and that's kind of very important. So trying to make developers and validation or QA work together is even more challenging than in other places. And also, the business needs to also understand the limitation and how you can mature as an organization on doing that. So Industry 4.0 and the whole IoT is a thing that a lot of executives will talk about, and they are really excited about that. But then there is there has to be a really big investment on how you support and how you upskill development teams, and how you skill yourself as a developer to be able to learn new techniques and learn new practices and be comfortable with all of these changes. And that was it. Thank you.